So I just want to point out that next class, Friday, is our first quiz. It's going to cover classes 1 through 4, so everything up through today. And again, Project 1 has officially been assigned. It's posted in Moodle, and it's due a week from Monday. It's due this upcoming Monday. Okay. Any questions? Yes. Whichever you want. You can bring it in. I was just expecting it in class, but I can put up like a submit your project here button on Moodle if you want. Okay. All right, let's see. Where are we? Class 4. Okay, class number 4, the derivative at a point. Before we start, anybody have any questions on previous material or anything that you want to talk about? Okay, I did put solutions to the 5th edition text in the Math Studio. I'm waiting on the 6th edition one still, and some binders, and I'll get them in the Math Studio in the library. But I did post them in Moodle as PDFs, so you can see them there right now. All right, so today we're going to talk about the derivative at a point. So we have not yet used the word derivative, so today is where we unveil what that is. Okay, so suppose that the height of an object is given by s of t equals t squared plus 2. I want you to find the object's average velocity from t equals 1 to t equals 1.1 and t equals 1 to t equals 1.01. So take 3, 4, 5 minutes in your groups and calculate these average velocities. Okay, so remember, we calculate average velocity by taking change in distance over change in time. Change in position divided by change in time. So change in position divided by change in time. And the height of an object, that's its position. So I'm going to calculate the change in position by calculating its position at 1.1 and its position at 1 and subtracting. So I'm going to do s of 1.1 minus s of 1 over 1.1 minus 1. So s of 1.1, 1.1 squared plus 2. Okay, so s of 1.1 is 1.1 squared plus 2, so it's 3.21. And s of 1 is going to be 3. 1 squared plus 2. And 1.1 minus 1 is 0.1. So this comes out to 0.21 over 0.1, which is 2.1. So there's our average velocity over a small time interval, 1/10 of a second. And now we're going to make that time interval even smaller. Right now I'm going to go from 1 to 1.01. So I have s of 1.01 minus s of 1 over 1.01 minus 1. What's this? 3.021 maybe? 1.01 squared plus 2. 3.0201. Minus 3 over 0.01. So 0.0201 divided by 0.01, what's that come out to? 2.01. So what would you guess, just based on these two average velocities over small time intervals, what do you guess the instantaneous velocity is? 2. Yeah, you might conjecture it's 2. So we're going to find with algebra the instantaneous velocity at t equals 1. Okay. We're not going to guess it. We're going to actually calculate it using a limit. So remember, average velocity from t equals 1 to t equals a little bit more than 1, and we're going to measure a little bit more than 1 with the value 1 plus h. So h is representing that small amount, either 0.1 or 0.01, and we're going to let that h get really, really small. So we calculate that with s of 1 plus h minus s of 1 all over h. So h is your change in time. From t equals 1 to t equals 1 plus h, your change in time is just h. So when I plug 1 plus h into my s function, I get 1 plus h squared plus 2. That's my s of 1 plus h. And then I plug in what I get when I plug in a 1, which was 3 all over h. So that first part in the square brackets, that's what you get when you plug in 1 plus h. And the 3, that's what you get when you plug in 1, both into the s function. I'm going to simplify that expression. Just do some squaring and some combining like terms. So 1 plus h squared, that's 1 plus 2h plus h squared. And I'm going to add the 2. So I have h squared plus 2h plus 3. That's what's all in the square brackets. Then I have the minus 3 over h.
Your first figure is plus h squared plus h, not squared, squared.
The formula for s, which is up here.
Okay, substitution.
Yes, I was substituting 1 plus h into the s formula. Yep. So this was function notation. This says s evaluated at 1 plus h, plugging my 1 plus h into the formula. All right, so then continue to simplify. I have a plus 3 and a minus 3, so those cancel. And my average velocity from 1 to 1 plus h is going to be h squared plus 2h over h. And then what do you notice? You can cancel, yeah. So I could rewrite my numerator as h times h plus 2, factor out an h. And then my h's cancel, one on the top, one on the bottom. So my average velocity is h plus 2. Need a little more room here. Okay, so I did all kinds of not too difficult algebra, just making it look prettier, right? So the whole purpose behind that is that now I would like to know the instantaneous velocity when t equals 1. So if the average velocity from 1 to 1 plus h is given by that expression, to find the instantaneous velocity, I just have to let h, the time interval, go to 0. So I'm going to take the limit as h approaches 0 of my average velocity of h plus 2. So what happens to h plus 2 as h goes to 0? It equals 2. And that is exactly the value that we guessed from the two average velocities that we calculated. So that's how you calculate an instantaneous velocity algebraically. You calculate an average velocity, and then you take the limit as the time interval h approaches 0. So everything that we've done so far with velocities over the past few classes can be applied also to arbitrary functions, not just height or distance functions. So it doesn't have to be just distance and time. For a general function, instead of average velocity, we say average rate of change. Right? So velocity is just a special word that talks about a change in distance with respect to time. But if we're not dealing with a distance time function, we can just say it's an average rate of change. And instantaneous velocity becomes instantaneous rate of change. Okay, so instantaneous rate of change. For a given function, y equals f of t at time t equals a. So a is some point in time that you're interested in. This would be like a number, right? Is given by this limit. The limit as h approaches 0 of f of a plus h minus f of a over h. So f of a plus h minus f of a over h, that's giving you an average velocity over time interval h, and then we let that time interval decrease to 0. All right, so you have the population P of t of China in billions can be approximated by this exponential growth function, where t is the number of years since the start of 2000. I want you to use the model to estimate how fast the population was growing at the start of 2013. Rounding P of 13 is a bad idea, just to give you a little heads up there. And at the start of 2000. So again, I said estimate. So you're going to be calculating average rate of change over a suitably small time interval. You can decide what suitably small is. All right, so let's discuss it together. We'll do 2000 first. And we'll do 2013 over here. Okay, so we're looking for an average velocity because we're trying to approximate or estimate how fast the population is growing. That is the rate of change of the population at the start of the year 2000. So we need to pick some small time interval near or around the year 2000 to get an average rate of change. What time interval did people use? 1 year? A thousandth of a year? So you went from t equals 0 to t equals 0.001? Oh, okay. So you went a little bit before 2000, a little after 2000? Sure. So 1 year is an awfully long time interval. When you're trying to get an instantaneous at a moment rate of change, 1 year is pretty long. So we might shorten that a little bit to a tenth of a year. That's like a little more than a month. Yeah. So that would be a better estimate, or 100th of a year, or 1,000th of a year, something like that. So I'm going to do, I'm going to use t equals 0, which represents the year 2000, right, to t equals 0.01. So we kind of have the, and so it's perfectly acceptable also to go say like t equals 0.99, or sorry, negative 0.01 to positive 0.01, and like get an average rate of change that encompasses, so that your time interval encompasses the year that you're interested in. That's fine. It's really just a personal preference, and when they ask you to estimate and don't tell you how, you're left to your own, make your own choices about the best way to estimate. Okay, so it might be that one is more accurate, but it might be that another is easier, right? So you just have to choose what is better for you. Okay, so I want my average velocity over this time interval. And I'm going to do P of 0.01 minus P of 0 over my time interval, which is just 0.01 of a year, 100th of a year. And now I'm going to take this opportunity to show you some fancy calculator stuff that you may or may not have already seen. It's just going to save us some calculation time and writing things down time and maybe some rounding error. save us some rounding error. So I'm going to go to my y equals and type in the function for the growth function. Here we have 1.267 times 1.007 to the t. I don't have a t, I'll use an x. All right, so now I want to evaluate this expression. I can do this whole thing in my home screen in one calculation rather than having to evaluate each of them, subtract, copy down all the decimal places. All right, so I'm going to go back to my home screen. And the way I'm going to have my calculator evaluate the function at those points is I'm going to use the y key, right? So it's in vars. You go to vars, first stands for variables, which makes sense because we're looking for the y variable. So you go vars, and then choose y vars because we're looking for y. And then option 1 is function. Yeah, we want to look at our functions. So you choose option 1, and all your y's are listed there, and I'm going to choose y1. And I'm going to say, okay, evaluate that at 0.01, parentheses. Open a parentheses and type in 0.01. It's just like function notation. Your calculator knows function notation. So y1 parentheses 0.01, your calculator knows that means plug 0.01 into the y, into y1. Then I'm going to subtract, and I'm going to do the same thing again. I'm going to call up a y1, and this time I'm going to evaluate it at 0. So you have vars, y vars, function y1, this time parentheses 0. And you can hit enter. So now we have the change in population size over 100th of a year. And I'm going to divide by my change in time, 0.01, and I get 0.00884 approximately. Or maybe I'll just leave it as 0.0088. So it's approximately 0.0088. And now my units here, p of 0.01 minus p of 0, my p's give me population sizes, right? In millions of people. So this is millions of people. Is it billions? Thank you. Billions of people. And this is years. So this is billions of people per year. And they asked me to give my answer in millions of people per year. So what is 0.0088 billion? How do I change that to, how many millions is that? 8.8, yeah, 3 decimals to the right will get you millions, which is 8.8 million people per year. Yes.
For homeworks, quizzes, exams. So is that supposed to do all that work in a calculator and not show it in the calculations?
As long as you have this, right, so I can see what you're calculating, it's perfectly fine. Yeah. Okay, so now we're going to do a similar thing for 2013. Let's just use the same approach where we use a 100th of a year. So I'm going to go from t equals 13 to t equals 13.01. 100th of a year, pretty small, relatively small time interval. So my velocity average is going to be p of 13.01 minus p of 13 over 0.01. Okay, so vars, y vars, function y1 evaluated at 13.01 minus vars, y vars, function y1 evaluated at 13. Small number divided by 0.01, 0.009677. And again, that's in billions of people per year. Move the decimal 3 to the right. So I get 9.677 million people per year. And I could have gotten better estimates for the instantaneous rate of change. How? Make your interval smaller. Regardless of how we set up our initial interval, whether you jumped over like negative 0.01 to 0.01 or 0 to 0.01, making it smaller in either instance will always give you a better estimate. All right, so this limit, this thing that we've been calculating, which we've been calling instantaneous rate of change, has a special name, and it is called the derivative. Okay, the limit as h goes to 0 of f of a plus h minus f of a over h. It's called the derivative of the function at x equals a. Note that the independent variable is usually x. We've been working with t a lot because these have been functions in time, but it's generally x, so we're going to use x now instead of t. So it's called the derivative. It represents the instantaneous rate of change. And the notation we use is this f apostrophe a, which you read as f prime of a. Means the derivative of f at a. Derivative of the function at a, or instantaneous rate of change. So to summarize, this is our most important definition of the semester. The derivative of f at x equals a is f prime of a, and we calculate it by taking a limit, which gives us an instantaneous rate of change. Finding the derivative of a function is known as differentiating the function. And if a function has a derivative, the function is called differentiable. So all of these phrases are important, and they will become second nature to you very soon as we do more and more work with them. So as we've seen, the average rate of change is the slope of a secant line. And as h goes to 0, that secant line becomes a tangent line. Good. So we're going to take a little look at a geometrical interpretation, little animation. Okay, so here's f of x equals e to the x. Pretty simple function. I want you to estimate f prime of 0, the derivative of the function at the point x equals 0. So I'm going to let you discuss a strategy on how to estimate that. All right, so I'm interrupting, sorry. I've seen two approaches, right? A numerical, based on what I've been drilling into you for the past 3 classes, and a graphical, based on the sentence that we just said like 3 or 4 times, right? So you can do it either way. They're both totally acceptable options because it says estimate, right? So you got to come up with an estimate for the derivative at 0, which we know is the instantaneous rate of change, and we've been doing that via an average rate of change, a difference quotient, letting that difference quotient get closer and closer to 0. So that totally makes sense that you would go to that because we've been doing that for several classes now. So maybe you would do f of 0.1 minus f of 0 over 0.1, something like that, right? That would give you an estimate of f prime of 0. Or you could remember that the derivative of a point is the slope of the tangent line at that point. So we could go to my point, 0, x equals 0, draw a tangent line, and estimate its slope graphically. Right? What does it look like the slope of that line is? 1. We would say m approximates f prime of 0, the slope of the tangent line. Well, it is the slope of the tangent line, but we're having to estimate what that slope is. Okay, and we approximate that at 1 based on our picture. And then let's just make sure that our numerical approximation gives us something close to 1, because these are just two approaches to answering the exact same question. So I'm going to do e to the 0.1 minus e to the 0 over 0.1. I get very close to 1, 1.05. And if I had done a smaller time interval, I'd be even closer to 1. Okay, so visually here we drew the tangent line, whose slope is the derivative. What does this approximation, this numerical approximation, how would I represent that graphically on my picture? So this difference quotient that we calculated, what does that represent graphically? The derivative is the slope of the tangent, but this is not, this is a secant line that connects what 2 points? 0 and 0.1. Yeah. So it connects this point to some point, you know, just a teeny bit to the right of it on the graph. So it's like that secant line, which is just a little bit steeper than my purple line, the tangent line. Probably not even that much steeper. I drew it to try to make a point. Okay, so this part of the question got cut off in your packet, so you're going to have to write it down. Here's a graph of f of x equals sine x. Gave you about 1 period, negative pi to pi. I want you to list these numbers from least to greatest, f prime of 0, f prime of 2.4, and f prime of negative pi over 2. So use whatever means you want to figure out which of those is smallest and which of those is biggest. Okay, so derivatives are slopes of tangent lines. F prime of 0 is the slope of the tangent line at 0, tangent to f at 0. So I go to 0 and I draw a little tangent line. Its slope is f prime of 0. And then f prime of 2.4, I go to 2.4, draw a little tangent line, and its slope is f prime of 2.4. And then f prime of negative pi over 2, where on the graph is negative pi over 2? Yeah, it's like, it's this low point, this minimum. Yeah. So the slope of that tangent line is f prime of negative pi over 2. So I have a 0 slope, a positive slope, and a negative slope. So my smallest would be the negative, which is f prime of 2.4. And then my middle would be the 0 slope, f prime of negative pi over 2. And then my biggest is going to be my positive slope, f prime of 0. Smallest to biggest. So we'll take a quick look at another geometer sketch pad just to verify. This calculates the slope of the tangent line. And can I move this point around? Whoa. Okay, so last thing we're going to do is use the limit definition of the derivative to find the f prime of 2 for 1 over x squared. So that is, I want to find the slope of the tangent line, the line that's tangent to 1 over x squared at x equals 2. And maybe I should just, just remind myself what I'm doing. So 1 over x squared looks like this. So I'm looking for the slope of the tangent line at x equals 2. So I go in 2, and I'm going to find the slope of my tangent line. So what can I say about it right before I even start? What do I think I'm looking for here? A negative. Yeah, I think that the answer is going to come out negative. So let's look for the slope of this tangent line algebraically. Actually, before we do it algebraically, let's do it numerically, right? So how could I, so this is graphical. The slope of this guy is f prime of 2, right? And then numerically, I know I can estimate f prime of 2 using a rate of change over a small time interval. I could do, say, f of 2.1 minus f of 2 over 0.1, something like that. And I could get a numerical approximation. This is approximately equal to f prime of 2. So let's just calculate that out just to see if it jives with the idea that we're going to get a negative slope from the picture. So 1 over x squared. 1 over x squared. So y1 at 2.1 minus y1 at 2 divided by 0.1, negative 0.23. Okay, so it came out negative. Which matches the idea from our picture that it should be negative. So we have two ways of wrapping our brain around what f prime of 2 means. It's the slope of the tangent line. We calculate it numerically by taking an average rate of change over a small time interval near 2. Or we could do the algebraic limit definition of a derivative. Okay, so the algebraic limit definition of a derivative says we're going to take a difference quotient, which is an average rate of change from t equals 2 to t equals 2 plus h, some distance in the future. So I'm going to do f of 2 plus h minus f of 2 all over h. That's an average rate of change from t equals 2 to some small distance in the future, 2 plus h. When we did our numerical approximation, we just used h equals what? 0.1 in this particular case, yeah. So, but then what I have to do is I have to take the limit as h approaches 0 of this whole thing. That is exactly f prime of 2 when I take the limit. So I'm being very careful to keep my notation as I go through. I'm going to write limit at every step, which I would expect you to do on a quiz or a test. Because if you leave the limit out, they're not equal anymore, right? So it's a picky little thing, but make sure you write it down every time. So now I'm going to plug 2 plus h into the function f. So this is 1 over 2 plus h squared minus, I'm going to plug 2 into the function f, which is 1/4 all over h. And I'm going to need some more room here. Oh, that's so annoying. Oh well. So again, I write down the limit as h goes to 0. And now I'm just going to simplify. 1 over 2 plus h squared. I'm just going to square my 2 plus h. This is 1 over. When you square 2 plus h, that's 2 plus h times 2 plus h. You got to FOIL it out. It's very tempting or easy to forget when you're in the midst of a really big calculation. It's really easy to write 4 plus h squared when you know very well that that is not true. So this is 4 plus 4h plus h squared minus 1/4 all over h. So now what's in the square brackets now? I'm not even going to try to take the limit until I have done as much simplifying as I can possibly do. Because right now, if I was going to try to take the limit, the first thing you do is try to plug in, and I end up with 0 over 0, and I can't do that. So I have more algebra to do before I can try to do the limit. So I have this complex fraction here. Let's just work with the numerator. Just the numerator of that fraction. I have two fractions I want to subtract. How do you subtract two fractions? You need a common denominator. What's my common denominator going to be? That's part of it. Times 4. Yeah. So one way to get common denominators is to take your two denominators and multiply them together, right? Same thing. Same thing. That's just a method of getting a common denominator. Okay, so the limit as h goes to 0 of, I'm going to multiply my first fraction times 4 over 4, and my second fraction times 4 plus 4h plus h squared over 4 plus 4h plus h squared, so that I will have common denominators. All right, 4 over 4 plus 4h plus h squared minus 4 plus 4h plus h squared over, oh, sorry, there's a 4 here. This is still all over h. I'm just carrying it along for now. Everybody okay with how we got there? Common denominators? All right, so now that we have the common denominator, the whole purpose of a common denominator is that now you can just add the numerators, right? Or subtract the numerators. Yeah, so I have 4 minus 4. The 4's go away. And then I have to distribute this minus sign to everything else in there as well. So I have the limit as h approaches 0. 4's go away, and I have negative 4h plus h squared over my common denominator, which is 4 times 4 plus 4h plus h squared all over h. Yes, thank you. Negative 4h minus h squared. Yeah, I made a big deal about saying distribute the negative, and then I didn't do it. Okay, so I still have a complex fraction. I have a fraction divided by h, right? Instead of dividing by h, how could I rewrite it as a multiplication? Flip it. So instead of dividing by h, I'm going to multiply by 1 over h. Just like dividing by 2 and multiplying by a half are the same thing. Right? So I'm going to rewrite this as the limit as h approaches 0 of negative 4h minus h squared over that common denominator, 4 times 4 plus 4h plus h squared, all times 1 over h. All right, what else can I do now to simplify that expression in the brackets? Take an h out of the numerator, cancel it with the h in the denominator. So I'm going to cancel h, h, h. So basically I rewrote the, I'll write the whole thing out. Might as well. I'm going to take out an h, and then we'll be left with -4 minus h over 4 and then that h and that h cancel. Now that I have canceled the h that was originally in the denominator, now I can plug 0 in for h. I now am not going to get 0 over 0 anymore. So when you take the limit, you don't have to write limit anymore when you put in the 0. So I'm going to have -4 divided by the 4h and the h squared. Those are going to go to 0, so I get 16, and I get -1/4. So it is negative, and it is close to the -0.23 I got when I did the numerical estimation, but this is the exact value of the slope of the tangent line at 2. These derivative calculations are long and tedious. I am going to make you do them for a few classes. Then we will learn some shortcuts, right? But the whole, what good is a shortcut if you don't know how much work you're saving, right? You're going to do the work first. All right, so that finishes up class 4. Your homework that's due today is classes 1 and 2. So if you can just make a pile of those on your tables, I'll pick them up after you leave.